So, for example, look at this thing here. This is almost molybdenum D. And what I'm saying is, why am I doing all of these things? Because we found, by trying to help Balikas explain his quantum oscillation data, that if we shift the hole pockets in one direction and the downwards, and the electron pockets upwards, we can get much better agreement. We can explain some of these things by a simple shift. And people say, why are you shifting things? And the motivation for shifting is that if you look at this orbital character of the DFT bands, you say here is molybdenum D, and this is P. Everybody in correlated electron community knows that if you have D electrons are more localized, and so when you put two electrons on the same d orbital, they sort of push each other because of this localization, and there is this on-site Coulomb. And so obviously this band here, which is only like 50 millieV below the Fermi level, if you put a U of the order of a couple of V, this pushing is going to elevate this electron state upwards above the Fermi level and might go away, because you don't want to have all this complexity. As I said, all these things here disappear right away. These pockets here, which are in DFT, disappear right away, and things become simpler. And it amounts to shifting things up and down by doing that, because the d orbitals will be shifted upwards, because every time an electron occasionally visits that orbital, and because the wave function has some non-zero admixture with that orbital in its block state, is going to feel the presence, the occasional presence of another electron. So in a mean field sense, its energy of that orbit, of that band that has a lot of admixture from that orbital, is going to be elevated. So that's the motivation why we think perhaps we can explain this, hopefully without missing the Weyl physics, and it happens to be the case, actually. So we did this. This is the most general Hamiltonian you can have for two orbitals, the most general tight-binding Hamiltonian. You have diagonal metric ceremonies depend on K, and then off-diagonal metric ceremonies have real and imaginary parts. This is the most general Hamiltonian you can write for two orbitals, tight-binding Hamiltonian. And then we can transform this in sort of this vector H dot a pseudo-spin operator, Pauli operator, pseudo-spin because of the A, B orbitals, the D and the P. A will stand for, say, P, and D will stand for D orbital. As a result, you have a pseudo-spin here. Pseudo-spin means up spin means P orbital, and down spin means D orbital. And you end up getting something like the classic form for a Weyl fermion. If you linearize near the zeros of this, so you have to have, this thing has to have zeros in order to get Weyl particles. And if you happen to have zeros, and this is possible in, this has three components, it's a vector, so you have to make all three components zero at the same time. And we said this kind of accident, to be able to solve this, to find non-zero solutions to three equations with three unknowns, the unknowns will be kx, ky, kz, is quite possible. So it's quite possible to have solutions. Each one of these equations represents a surface in 3 dimensions, a surface, like, for example, the Fermi surface, this type of surface. And it has to be intersected by another surface, and that will define a line. And then a third surface has to come in, and that line has to be intersected by that third surface, which is, again, quite possible. And so that will define your Weyl points. So we said in 3 dimensions, it's not, given the fact that you have a Brillouin zone which is bounded, and you have plenty of bands going around inside this small room, finding Weyl points in any material, it wouldn't surprise me. The only question is, are they going to be relevant? That means, are they going to be giving you the low energy physics of the problem. That means, will they be close to the Fermi level? That's the only question. But if you go to lower dimensions, this kind of accident is not going to happen easily, because you will have still 3 equations to satisfy, but you only have kx and ky. So you have 2 unknowns to satisfy 3 equations. You must be lucky in this case. And in 1 dimension, you must be even luckier. So these bad accidents, as bad points, as Ed Witten is calling them, these Weyl points or diabolical points, won't happen to you if you live in low dimensions. If your life is pretty simple, if you don't move around too much, you're not going to have accidents. And so then we introduced, to understand what's going on, this Hubbard term, and we just did mean field decomposition, and this adds only because it's only on the A orbital, let's say. A orbital was the D orbital, sorry. That's where you add this term in this thing, which amounts to, this would be H1, this would be H1, and this H1 is, has to be 0, has to have a 0, that must be kx, ky, kz, which makes this 0, and that 0 now is changed by this constant term added into the diagonal term, and that pushes these things when you have this intersection. This is 2-dimensional. Let's say you have this line here of intersections. You can eliminate altogether this intersection by adding some significant value of u, but it doesn't have to happen like this. In 3 dimensions, you have, this is the surface, let's say, which f1 goes to 0. Then with u, you reduce this surface, and then if you put a larger value of u, you reduce this surface of common points just for the diagonal, just for one of the constraints that you have to satisfy. But then if you bring a second constraint, then as I said, it's the intersection of these 2 supersurfaces here. But by reducing, by putting a u value, you're reducing this. So you miss the contact with the other one, so you don't have a Weyl point anymore. Easier than just completely shrinking the first surface to 0. So you can eliminate or produce Weyl pairs by, in a simple way. Of course, this is mean field, but also the concept of topology is one particle concept. And so this mean field treatment of this Hubbard, if you like, or GGA+U, which is kind of a mean field, self-consistent mean field, is the way to actually continue this language of one particle picture that exists in topology before you get into quasi-particles and response functions, and whether you have well-defined poles in the single particle Green's function, and if they have non-zero residue and things like that, and define a vocabulary to go beyond this type of like going to something like Landau Fermi liquid theory or Landau or something equivalent to that when you are talking about topology. So well, my point is that this back in the envelope is the only way at the moment where things are clear in terms of mean field. And we can see that in mean field, not what I mean is they don't disappear right away by introducing any u, because these things, these solutions, if they exist in a range, and they have this range is the core of their robustness. But you can crank up u to some value, you're going to end up not having them. So that's the danger of correlations. And the fact that we don't agree at the with the experiments puts this whole thing into some sort of doubt. And this was raised by us with these experiments done here. And that's why we did the GGA+U, to see if at least the Weyl points are safe. And so the open circles here are with 0 u, that means GGA, generalized conjugate approximation. You can also do the simple LDA if you like. Actually similar. But then you crank up u, you take u equals to 3 or 5 to just see if there is a significant difference. Not much difference here. You can see a huge difference here, the thing that I was telling you about, that because these guys here are pure D character, are pushed up, and they lose their occupancy because they're above the Fermi level, so the electrons now empty these pockets and fill holes, and as a result, what happens at the same time, you lose some of the electron pockets, and at the same time, you reduce the hole sizes of the hole pockets because they get filled. And you can see that you know, the number of Weyl points, because you have plenty of Weyl points, you have 12 or something. As you crank up U, they go down, and then you get more, you get 8, then you get 4, then you get 8 as function of U. So they go away in pairs, but and the Fermi surface is changing with value of U. This is 3. Here it looks this big hole pocket, and here you are getting some different structure. It looks like, you know, I don't know, a head with ears, and all of a sudden those ears disappear from the head. It gets smaller, and this is some sort of a Lifshitz transition happening at 5, or less than 5, 4 point something, 4.2, U equals to 4.2. You get a very significant Lifshitz transition. In the meantime, for smaller Wies of U, for a small Wies of U, you can call this a Lifshitz transition too, when you lose these ones, and you also lose one hole pocket in the middle of this. And but as I said, this is now a slab calculation, so you can see the Fermi arcs. This is U equal to 0. You have this huge gigantic hole pocket, which is not what they see in quantum oscillations by no means. If you calculate the frequency for quantum oscillations, will be in the thousands. It's going to be 1,500 or something Tesla for this whole pocket. And so this is completely unreasonable for quantum oscillations. This U equal to 0 picture of the Fermi surface.
So the U that you add here is not the same as the U you showed in the mean field model, but have there been some studies for sort of understanding how this U and that U are sort of possibly related, or they are completely unrelated?
No, the other one is not. The other one is just a schematic thing. Is to show you the structure of what's going on. It's not. Just don't take seriously these pictures which I show you over here. These pictures are just very schematic to tell you what happens, how you can lose the vileness of this. So there is nothing, there is no calculation here. This is a schematic. This is the calculation. This is the calculation, yeah.
So that was just done.
Yeah, but it's the same sort of thing. What you do in GGA+U is you just have a functional now, which is a function of up and down densities, and you just do a local, you're solving your differential equations for different, you have a functional now, a generalized functional by which you have also introduced this U term in the functional, and just solve that problem self-consistently. So it's, some people take it serious and say, what's the actual value of U? That I have to use. I'm not taking that point of view. What's the value of U? Is what can I see by varying this U, and is this resembling the experiment? That's our point of view. Of course, we can do something about computing this value of U, but you're taking your life very seriously. And you have more serious problems like this problem, which I pointed out to you, that even ARPES has polarization dependence. How can we understand this polarization dependence? And as I said, ARPES has also this structure that looks like ears with a head, but the head is in this polarization, which is vertical. The light polarization is vertical. There is no head in the center. It's not bright. Here you have a head, but almost the ears are gone. We had to put these dots by hand in order to help you guide your eyes to see the ears. So there seems to be that there is some strong polarization dependence of the ARPES results. And that's what we're going to address right now. I think we are going to look at this issue of polarization dependence. So can we do a calculation with polarization dependence? The answer is no, but we can calculate what matrix elements are 0 and exclude them from a given polarization of light. So we can use Wigner-Eckert theorem and say this particular orbital content is not going to contribute to this polarization of light because the operator that enters in the ARPES intensity, this is the famous spectral function, single particle spectral function, the imaginary part of the Green's function. And there is the matrix element, which is the coupling of the dipole operator to this is the matrix element of the dipole operator between initial and final state. Initial state is the state inside your crystal, and the final state is what you observe at the ARPES detector. So the outgoing electron, the photo-ejected electron, is typically in typical scattering geometry of ARPES, is parallel to the surface, in this case the xy plane. And therefore, it's a plane wave. This electron that is detected by ARPES has only kx and ky momentum. This is well known. Now, if you take the initial state, which is what's going on in the crystal, take the Bloch state from the crystal where the electron is coming from in its way to your detector, and you expand this into some local basis. This is very general expansion. What you have is you have this, except the radially symmetric part, you also have this px, py, pz, or dx squared minus y. You have these angular, the orbitals, if you like. And you have this px, py, pz, but from the 5Ds, you have the dz squared, dx squared minus y squared, the dxy and dxz and dyz. Not all of them contribute equally to the intensity, to the ARPES intensity. It depends on the polarization of the light that ejects out the electron. So because of the fact that this is an even function, this radial part is even with respect to parity, is an even function of x, y, and z. And the final state is only a function of x and y, and the operator that we are interested in is this operator, which is a vector operator. You can show easily that the matrix elements that contribute to ARPES for polarization parallel to the z-axis are only from the p orbitals, only the pz orbital, and from the d orbitals, only the dxz and the dyz. You have to have a z component in order to get contribution to the z polarization ARPES intensity. And when the intensity, when the light that comes in has a polarization which is parallel to the surface, parallel to the xy, then you have the px and py, p orbitals contributing, and the dx squared minus y squared and the z squared orbitals. The other orbitals don't contribute. So don't add them when you do DFT calculations and you say, I'm going to take the point of view of just taking the density of states and this is all, I forgot yesterday to mention, this is on the archive, but now we just got the proofs, so we are sending the corrected proofs today. So it's going to be published hopefully in a week or something. And now here is the data. These are the data for ARPES. This is vertical polarization, light vertical, and this is horizontal polarization for light. And this is the top line. This one here is DFT. Is insensitive to actually to the polarization, the DFT calculation. I mean, there is some dependence, of course, but not significant to explain this thing here. The central hole pocket is barely unchanged, by that. But if in the GGA+U with U equals to say 3 or something like that, not only we get this kind of structure which is more, the central pocket is thinner than than in the DFT. But also, if you look at here, this is bright for vertical polarization. The central plot is right. And the ears are faint in the GGA+U. And on the other side, when you go to horizontal polarization, this becomes faint as it is in ARPES. And the ears become more visible. So maybe there is some truth to this back in the envelope calculation. And maybe Balikas is not so crazy. And so now if we look at the, don't tell him that I said that. So this is now his experiments for U equal to 0, 3, and 5 V. U equal to 0 is DFT. We discussed this is not making no sense. And for U equals to 3, though, you begin to see something, some agreement here. These things here were not there at all, but all of a sudden you get some agreement here. And the only things that still disagree for U equals to 3 are these frequencies here, but they may not necessarily be visible in, for some reason, in the quantum oscillation experiments. These are pretty large frequencies, and that means that maybe more dissipation. By the time you go around once around the Fermi surface, the electrons lose steam. They don't exist anymore because, again, the quasi-particle picture, you have to go into residues and stuff like that and see lifetimes. For how long these quasi-particles exist, do they have enough lifetime to go around the Fermi surface once? Maybe not. We are just doing GGA+U. These effects are not there. So there is better agreement, but if you go to U equals to 5, the agreement is even better with their measurements. But U equals to 5, it wouldn't agree with ARPES at all in some sense, unless the ARPES. So U equal to 5, I show you the Fermi surface for U equal to 5. Did I show U equal to 5 anyway? Here, U equals to 5 has a disconnected Fermi surface. The ears separate themselves from the core, the gamma point hole pocket. And it looks like this is, because of the polarization dependence, this is closer to ARPES. So if you want to be faithful to both worlds, I will accept some moderate value of U. And U equals 2 or 3, some value around there. But there is, as I said, a Lifshitz transition occurring at some value of U around 4.2. So, which means that, because this is not a serious calculation, that we are in that proximity. We are in the proximity of a very sensitive Fermi surface, ready to break up, ready to become topologically different. The Fermi surface to change its own topology and have more pieces. Yes?
Experimentally, do you know how they tune through different U?
Do U? They don't do U. No. They just do nature, and nature has maybe does not know even U. That exists in our head. So the U. Yeah, experimental plots. Yeah, those are. What is that? So these are experimental plots. This is for the real system, and we are looking at it as a function of. That's a good question. As a function of the angle. This is the c-axis, and this is a-axis. This is b-axis. So what he does is he's putting the magnetic field in different directions relative to the axis of your crystal. So if the Fermi surface has a, sorry for going back and forth like this, but I had these things here. So if you look at this is, let's say, a Fermi surface, and you put the magnetic field like this, you get this maximal cross-sectional area of the Fermi surface. So you get a CAT scan of the Fermi surface. Now, if you are going around say the other axis, completely like this, you will see if there is a closed orbit like this. If not, you will see some infinite orbit. If this continues the next Brillouin zone, the orbit is going to have an infinite size, and you can see the divergence of that with angle, and that's what they are doing. They are just putting the sample, which is crystalline sample, and they just change the angle of the magnetic field, and they are looking at the Chubin-Hall-DeHaas oscillations. And from there, you get the frequency. Then the frequency is related to the cross-sectional area of the Fermi surface. So it's the angular dependence that it exists as has existence as an experimental output, not the U dependence. The U dependence is our tool just to see are there correlations and how significant they are. And they seem to be not very significant in the sense that they're not, you don't have U equals 2. You're not in the strong U limit. Also, you don't have half-filled bands in this material. You have very, very tiny pockets here compared to this gigantic electron band here. And the whole bands are almost filled, and you only have a small fraction of that. So it's a small occupancy. And that small number gets multiplying a U of the order of 2 eV. You multiply by some small occupancy Hitesh, and that gives you a small number. It's not EVs, it's 50 milli-electron volts. But this is 58 milli-electron volts in this problem. And this Weyl point, which sits about 50 milli-eV above the Fermi level here. And the reason why I'm considering in this theoretical scheme just D and P orbitals is that because if you go away from this Weyl point, you see that this orbital here away is almost purely P. There is, D. There is no P, and it's almost the other one that hybridizes to make the Weyl point is almost purely P. So the rest have very negligible contribution, the rest of the other orbitals. So we have almost a two-band model in this, at least before you get to the Weyl point. Then at the Weyl point, these things hybridize. And any other questions? I keep on. Thank you. Yes.
Can you remind me if you include spin-orbit interaction?
Yes, the spin-orbit interaction. This is all with spin-orbit interaction. This is all with spin-orbit interaction. But the Weyl points present themselves even without spin-orbit interaction. So it's this, in the model that I have, is this pseudo-spin that gives rise to these Weyl points. So is this D, the hybridization between D and P that gives rise to the Weyl points. It's not the spin-orbit coupling that does that. And the spin-orbit coupling, I'll discuss that in a moment. Spin-orbit coupling splits these and makes them 4 instead of 2 pairs. Instead of 2, makes them 4. So let me just continue and go to the thing. Okay, so I think the angular dependence of the ARPES and the angular dependence, believe it or not, of the quantum oscillation experiments suggest that the correlations have some role and not terribly significant, but at the end of the day, what happens is the Weyl points survive. So in order to be able to see if they survive or not, you have to figure out the fluxes and of the Berry phase, and you have to figure out the sources and sinks, and those are this W1 and W2 on the k is equal to 0 plane. For some values of U here, just schematically for U equals to 0 and some finite value of U, you see that they move these Weyl points. They move. They move as in K space. Because there are some reports for the tungsten ditelluride claiming that they go away But they do go away if you crank up U significantly, but they just move, and they are not at the high symmetry directions. They hide themselves behind high symmetry directions, and you may miss them if you just plot your bands along high symmetry directions. You have to find the very curvature and figure out where it becomes singular. So there is this W1 and the W2 Weyl point, which is, this is W1 over here and W2. Here is W1 over here and W2 over there in the DFT. And so you can plot them along the W1, W2 direction. You can go and plot the bands along the direction of sink source, which are not really high symmetry directions in a crystal. And what you see is if you go along this W1, W2 direction, you see it looks like this became all of a sudden Weyl type 1. It's not the case that it becomes Weyl type 1. If you go into the direction perpendicular to the W1, W2 direction, to the source sink direction, but that direction perpendicular defines a plane. So if you take that plane and you take the intersection of that plane, first of all, that plane going through W2, you take that plane going through W2 perpendicular to the W1, W2 direction, and you find the intersection of that plane with the XY plane, and that's this direction which we are plotting it here. And you can see that this is now tilted. Now, W1 is not in that direction. So the direction, so here's W1, this is W2, right, in space. So we take the plane that goes through W2. So we are plotting along this direction, but there are many directions, right? So this direction we choose is on this plane going through W2, but that plane intersects the XY plane that defines a line. That's the line that we are using to plot it. There is no W1 along that direction. And you can see that the key here is that correlations apparently bring this point right on the top of the Fermi surface for this value of U that gives best of both worlds. So that's encouraging. Not only we remove the controversy created by the quantum oscillation experiments, but also the point is more relevant because it seems to be going right on the Fermi surface right now with this calculation. So it's probably a time now to do some more serious many-body calculation to see if things are there. Okay, so as I said, the fate of the Weyl points, they seem to be moving closer to the Fermi surface. Their number changes, but at the optimal value of U, which gives good agreement with experiments, the Weyl points are closer to the Fermi level, and at least you have those two that you like. And so at that value of U also we get some more reasonable agreement between ARPES and quantum oscillation experiments. I'll get to this conclusion, but let me talk a little bit about the other topic. I mean the interpretation of this in terms of some simple models, because the question is what's happening to spin-orbit coupling and things like that. People ask that question. So okay, so now I'm going to consider a simple model, this model with two orbitals, because you saw that there were only purely two orbitals, 95% probability for only just two orbitals. So those will be just P or D. And surprisingly or interestingly, their orbital character differs by one quantum. One is of angular momentum. One was P, the other one was D. So one is L equals to 1, the other one is L equals to 2. This is significant because spin-orbit coupling couples spin with angular momentum, and angular momentum now, the operator, when the off-diagonal part of it, if you write L dot S as LZ S Z plus a half L plus S minus plus L minus as L plus. So it has diagonal and off-diagonal matrix elements, the spin-orbit coupling operator. Couples P with D through off-diagonal right now. So it flips spins because it's spin-orbit coupling. At the same time, you go from orbital A to orbital B, from P to D, and vice versa. We will consider 2 bands, as I said, and take a model for Weyl points before spin-orbit coupling, and then you have this pseudo-spin chiralities. You have pseudo-spin chiralities. So the 2 partners are actually of opposite pseudo-spin chirality. Chirality related to pseudo-spin. Projection of, if you like, the D or B character onto the momentum direction. And then the spin-orbit coupling splits each of these Weyl points, these partners of opposite pseudo-spin chirality, into 2 pairs of opposite spin chirality. So it splits the pair into a quartet. And that's due to the spin-orbit coupling. Then we are going to add this on-site repulsion U, and we can see that the presence of this on-site repulsion U is to shift the Weyl points along the Z direction, and so they survive up to some moderate value of U. But then there's a critical value of U where we can see that the Weyl points go away abruptly. So we can see that within this simple model. So as I said, this is the lattice structure of this TD phase of this orthorhombic phase of the molybdenum ditelluride, and the unit cell is orthorhombic, and it has, so the unit cell has 2 layers inside, and they are related in such a way so that there is inversion symmetry broken along the z-axis. So you can see that in order to go from here to here, I have to sort of rotate myself by some angle in order to go to the top, to the second layer of my unit cell. This is equivalent to that, and this is equivalent to that, but those 2 things are not, there is no inversion symmetry between those 2. So I'm going to take a model which has Weyl points at k equals to k0. This is a 2-dimensional, so let's just do a 2-dimensional model first. So because it's this layer structure, and I'm going to take a Weyl point along the kx, ky direction, and this is the Weyl point. So I have a pair of Weyl points, because always they exist in pairs, and this is pseudo-spin chirality. I'm going to now focus on one of these Weyl points. I take one of these pseudo-spin partners, and I'm going to add spin-orbit coupling to that near the vicinity of this k point. So I take this k0x, ky0, some fixed value of k, and I'm going to introduce spin-orbit coupling there. So it's a 2-by-2 problem around that point. This is the pseudo-spin, and this means, the first row means D, and the other one means P, and they hybridize, and they give you this. Hamiltonian, the famous thing that's going to give you the spectrum of this will end up being, if you diagonalize this, it's going to be square root of kx squared plus ky squared prime, where kx prime is from this Weyl point, the distance from the Weyl point, not from the gamma point. Okay. Now, because I want to introduce spin, this has no spin. This is a pseudo-spin. Now I want to introduce spin, so I make my matrix 4x4, and this is A up, B up, A down, B down, and so I have a 4x4 Hamiltonian. And now I want to introduce spin-orbit coupling. And as I said, the key here is that the spin-orbit coupling enters along this anti-diagonal in this problem. It's some matrix element. I don't need to write that down. I'm not going. The results I'm going to discuss are qualitative, and they don't depend on the particular value or the form of this lambda of k. as long as it's along this anti-diagonal. I don't have any matrix element along these points, that's what I'm trying to say. Because, as I said, this spin-orbit coupling couples A-type orbital with spin up with B-type orbital and spin down, because A and B have different angular momentum content, and they differ by a unit of 1. So I can flip angular momentum, if you like, and at the same time flip spin because of this operator here. I flip spin and angular momentum at the same time in this case. And this gives you 0 contribution because it's off diagonal in spin, at least in spin. That's enough for you to get a 0. So with this assumption, this is the form of my Hamiltonian. I can do this, believe it or not. I can diagonalize this easily, and I just shift the Weyl points. But I shift them, I get from one Weyl point, there's the other one, I'm only focusing on one. So that one now becomes 2, splits into 2. And the splitting is along the kx and ky direction. The first one is minus this real part of this spin-orbit coupling, and the ky is the imaginary part plus the imaginary part of this spin-orbit coupling. If you don't have imaginary part, then you don't have shift in the ky direction. But you have only shift by plus or minus the real part. So you split this into, so you have one Weyl point. I mean, the other one is over here from pseudo-spin. So this particular one that's partnering in pseudo-spin space with the other guy, this particular one splits itself because of the spin-orbit coupling and creates a partnership, creates a pair of opposite spin chiralities, real spin chiralities, and they split in K space. So this is for 2 dimensions. Now I can generalize this in 3D easily. It's not, I mean, by simple 3D model. First of all, in 3D, I may have off-diagonal matrix elements. I can have here EA, EB, because I have 2 orbitals, A and B. But I can get out the center of mass of these 2 energies and have an identity matrix. And I can leave the difference relative to the center of mass of these energies. And I have here delta AB minus delta AB plus delta AB minus delta AB. And this Hamiltonian can be diagonalized. And I get this center of mass here. And here I have the standard thing that can only become Weyl if this delta AB is 0, if this is 0. So in general, if I don't have a k-independent diagonal term, I must be extremely lucky. I must have no gap for some reason. But even the spin-orbit coupling can give you some diagonal contribution, constant contribution, k-independent contribution. So it seems like difficult thing. The Weylness goes away right away. It looks like if I have in 3 dimensions some diagonal elements like this. The point, though, is that I can introduce hopping in the perpendicular direction. And if I do that, then let's say I introduce hopping between A orbitals and B orbitals independently. Then I can rearrange these terms again the same way by, adding and subtracting a constant. Constant, I mean, this is kz dependent, but it's diagonal constant. And this matrix now takes the same form as before. So if I diagonalize this one now, again, I get some kz dependent platform in which I move my center of mass in this, but the Weyl points are obtained when this gamma kz goes to 0, and this gamma kz goes to 0. It can go to 0 because now this is kz dependent. So here is the gamma kz, it can go to 0. This is non-zero, but because I put a kz dependent, I can ask the question, and here is the robustness of these things. Is there a kz where I can make this equal to 0? Before I couldn't make it to 0, but now I have a degree of freedom, as I was saying. I'm solving 3 equations with 3 unknowns in order to find Weyl points. And so I can find a kz value if, but this, remember, this is bounded because it's the dispersion. And so I have some limitations if I can find a kz value. This, if you like, this change between A and B in energy is bounded within my bandwidth of my kz-dependent band here, that this can happen. So I have some kz value provided that this is bounded by 1 and minus 1, this ratio. And so there is a window where the Weyl points survive. And, but now, okay, I have spin-orbit coupling. I want to add these correlation effects. So I go to this point where I have Weyl physics. So I make that term equal to 0, this equal to 0, and I have Weyl physics. And I say, well, what happens now? This is 0. It's a nice Weyl because this term here is linear square. So I get square root of kx and ky squares. Now I put a u. Your immediate reaction is that I'm going to completely lose the Weylness. So if I put only u on the a sublattice, as I was saying, because that's where the d orbital is, then this just adds a constant, as I pointed out to you. If I do mean field treatment of this, in the a orbital over here, I'm going to add a constant. But a exists here and exists there because it's the downspin sector of this Hamiltonian. And so now I get contributions to here. And I'm going fast because the time is running out. So I can add the constant here and here. And then I can do the same trick. I can put the same constant outside because this identity doesn't change the topological nature of this problem. And this is the matrix that I need to worry about. So I get some band, and on top of this band, I have this thing here, which might or might not be Weyl. So now I have this thing here playing the role of a gap, which might not give me Weylness, but again, this is kz dependent. I can change my mind about kz, what kz I take now. I can ask the question, is there another kz because I added this u? I add this u now. I add this u term. This is the u term that I'm adding. So where is this capital gamma? Z here. This capital gamma Z is the old gamma Z plus this constant from the u. And before it was, I found a kz where this was 0 without the presence of u in just normal DFT. I don't have this term. So I asked the question, what's the kz value that makes this equal to 0? There might be a value. Now I'm adding a constant. I asked the question, let's move this value of u to a different, shift it, find another kz so that this capital gamma is 0. And there might be one, provided that there is this thing that is bounded by 1. The absolute magnitude of that is bounded by 1. And so that is what we mean. There is some degree of robustness of these Weyl points. And so there might be a value of u, and that defines the value of u, where you have a critical region. Beyond that value of u, you no longer have a Weyl point. So you can play with these things and convince yourself that it's possible that correlations can actually eliminate these things, at least at this mean field level. And from this model, what are the conclusions? Is that we consider a simple continuum model, which discusses the hybridization of a p and a d orbital. We have pseudo-spin chiralities within this model, because this is also a case of MOT2. Without spin-orbit coupling, you do have Weyl points. Just like the Weyl points that Niraj showed you yesterday, that we had no spin-orbit coupling in those models, right? We got Weyl physics with just hoppings, no spin. So the same thing here. We can have these kinds of Weylness, and then we add spin-orbit coupling. So, and we have each of these Weyl points splits into pairs of real spin chiral partners. And adding U on that is not automatically things for any value of U, things get wiped out. You need a critical value of U above which the Weyl physics goes away. And these are the conclusions from the GGA calculations, which I showed you yesterday and I continued today. And we didn't need a huge value of U. Some people asked me during the break yesterday, how do I get the value of U? There are ways, and we are discussing these things with Hitesh, how to get a U value. There are ways, but we are only here interested if it's possible to explain what's going on in the experiments, and we found that a moderate value of U is enough to explain experimental data. And at the same time, we were lucky, Weyl physics doesn't go away. In fact, it improves the situation. It moves the Weyl points closer to the Fermi level. And we found two Lipschitz transitions. One is immediately with a very small value of U of the order of 1 eV. We found that some hole pockets and electron pockets just disappear. They move slightly above the Fermi surface, those pockets, because of the U. So, but they are not going away completely. They are just above the Fermi surface. And remember, those pockets were at some specific directions. So they may still, if DFT is finding them, it doesn't mean that DFT is completely wrong. It's just, it means they are near the Fermi level, those states. And they may be close enough so that they could be responsible for the giant magnetoresistance, because if you put a magnetic field, you are influencing the levels of these states through Zeeman coupling, and as a result, you change the carriers. You change the Fermi surface by magnetic fields. It's going to have anomalous properties, at least directional properties. And so one has to be careful when he does this magnetoresistance and claims that it's the Weyl points that are responsible for all these anomalous properties. One has to be careful that they are lurking pockets found by DFT, but they go away because of some small correlations. So there is one transition immediately, and then there is another Lipschitz transition which separates completely this central hole pocket into a small one in the center and its ears. And so all of these changes, this transition, they can be probed. Oops. They can experimentally be probed, perhaps by doping. By doping, you change the Fermi level, or by making devices and doing some other form of, making them two-dimensional, because those are, you can peel them off, you can use the standard approach that you do for graphene to peel them off, and you can create some layers, and you can do liquid gating and things like that, and you can dope them and see if you can probe these levels of Fermi level experimentally and see if all these things are there. So